Assalamualaikum, myself Muhammed with my team members Akif, Jawad and Faran Azam. The title of our project is Analyzing Football Passing Patterns Using Temporal Subgraph Isomorphism, a study based on dynamic graph analysis. First of all, I'm going to give you some information about my understanding of the dataset. The dataset represents passes made during football matches. Here is the dataset. This dataset has different columns. The first column represents the time at which the pass starts, and the second column represents at which time ends, and the third column represents the player's ID who made the pass, and the fourth column represents the player who received the pass, and the other column represents the position and location of 14 players of both the teams on x-axis and y-axis through the coordinate system. Now I'm going to give you a strategy for segregating matches. The first point is that iterative pass processing. The data set is processed sequentially, ensuring that the passes are grouped into the appropriate games. The key condition is that no two passes can be made simultaneously in the same game, avoiding ambiguity in edge assignment. The next point is ball possession analysis. For each pass, check if the receiver make a subsequent pass within 10 seconds. If yes, the receiver retain possession and a new edge is added to the graph. If no, the ball is considered lost, making the end of possession change for the sequence. This approach reflects realistic game dynamics, where possession changes are critical to strategy. The next point is tracking games. Passes are assigned to specific match using the game ID field in the dataset. Each game data is stored separately as a unique subgraph, ensuring a clean segmentation of matches. The challenges are ambiguous time steps ensure to overlap in edge creation for same game. And the next thing is missing data. Introduce exceptions to handle cases where data might be incomplete. Thanks for being here.
We talk about the Oberoi's code. Oberoi's code is built upon an enhanced version of Visual Feature 3, which is optimized for dynamic snapshots. There are two graphs which are mapped upon each other, and similarities are detected between them. Subgraph isomorphism is checked between constantly changing graphs, like the dataset that was provided to us, the passes in the match, which are constantly changing between different players. If we talk about the inputs of the code, that there are two different graphs that are taken as input: pattern graphs and target graphs, where pattern graphs are represented as the symbol H, and target graphs that are represented by symbol G. If you talk about the data input, this is the different data input that we use, and as an example of a target graph input is also shown over here, where there are 28 players and their names, also the passes that they played during the match towards to their teammates. And there's also a pattern graph input, that an example of a pattern graph input on which these passes are mapped upon uh, using the code. We used the passes, the different passing patterns. We mapped the different passing pattern of part on the passing pattern graphs, like the eight pattern graphs that are shown at the top over here, where and the frequency of how many times these pattern graphs occur in the data set are mapped on these charts, where the first pattern graph is almost always constant, because there's only one node over here, and there are 24 players. If there are 28 players in one match from both teams, and nine snapshots overall taken one half. So there's always a constant value. So the pattern graph one is always constant, whereas the rest of the pattern graphs are always changing. This is the strategy. This shows the strategies of one team in one match, and consequently in second match there's a similar strategy that the team has played. So now Akif will come.
First, now coming to the code, first of all, we have taken the input of the data set, and what we have done, instead of dividing the passes into the 14 matches, we have divided it into 28 halves as the time was started from the halves. So it was much more easier to divide them into 28 halves. So first of all, we have given the players attributes, like the player 1 to 14 that were belonging to one team were are starting from A, and the other team are starting from H. And so the total number of players in a one match were 28, including the substitutes. And then I have made a 2D vector edges, and these represent the passes between those players. And what I have done, that I have also made a 2D vector duplicate, which will make sure that there is no similar pass or the same pass that is made from one player to another, as the Ubera code gives error if the same pass is being made in a certain time snaps. So 2D vector keeps a boolean check of that. And then we have total number of passes, and I have divided it into 28 halves. And then coming to the total time interval, so which is 50, I have made I have divided the time interval into, I have divided the whole matches into 9 snaps, each of 5 minutes. So now coming to the code, so I have so what I do is that I read the whole row, and I made a function that turns that whole row into a string, to an array of string. And from there I check that who has made the pass and to whom it has made the pass. And then I check that is and there were some cases where the pass was being made to himself, so I have discarded it with the check. And also that I have also applied a check that keeps sure that no passes, the pass is being made to the same team instead of the other team, which will count as an interception. So here are K and I. K is used to keep track of the snaps. Like it will save the file after 50, and the I is is for the whole match. So after I is like 450, so it will create a new half, and and the new data will be stored in that half. So that was all the code. So now coming to the our results. So what we have run the code, and the, and we have mapped this pattern graph onto that our data set. So these are the pattern of the bourgeois. So first of all, these were the result, and the result of the first 4 matches, or of the first 4 halves, are here as a reference. So we can see, like, in all of the matches, that the pattern graph 8 is the most repeated one, is the frequency of those are the highest, and followed by the pattern graph 4 and 5. So these type of the passes were such as, like, you can see in the pattern graph 8, the player 1 passes to the player 2, and then player 3 and player 4. These sequence of three passes between four players is the most common in all of them. So, so we can conclude that these type of strategies are being made in teams. And also, like, you can see in the pattern graph 4, where player 1 passes to the player 2 and player 3, a sort of a triangle is formed. So this pattern is also very frequent in those matches. And now coming to the conclusion, that we have seen that the passing pattern of the graph 845 is the most common among 13. And these sort of analysis can help the coaches and different teams to analyze their game, and to prepare effective strategy against the other team. Thank you.
Now I'm going to give you the some related study to our project that enhances our interest in the project. The first is pass-wise analysis tool. The pass-wise is an advanced visualization tool developed to analyze soccer passes. which incorporates concepts like passing pattern, temporal dynamics, and phase evolution. This resource highlights how passing networks can reveal team strategy, defense adjustment, and offensive trends. The second related study is network science in football. Network science techniques such as clustering, dynamic graph analysis, and community detections are applied to study football passing networks. These methods help identify the mesoscale units in our team and understand the temporal evolution of game dynamics. Thanks for me.